Electromagnetism is a branch of physics, deals with the electromagnetic force that occurs between electrically charged particles. The electromagnetic force is one of the four fundamental forces and exhibits electromagnetic fields such as magnetic fields, electric fields, and light. Before invention of electromagnetism, people or scientists used to think electricity and magnetism are two different topics. Hi, hello. Today we are going to discuss about electromagnetism. In before 19th century, electricity and magnetism is considered as a different things. After doing Oester experiment, he proved that a current carrying conductor will produce a magnetic field. The conclusion is, if we send a current through a conductor, the magnetic field will be created surrounded by that conductor. That means we can produce magnetism by using electricity. After further research, we magnetism also produce current electricity also produced by using magnetism also. So that is, electricity and magnetism are at present is a interlinked subject. We can produce electricity by using magnetism. We can produce magnetism by using electricity. That is a conclusion we can make. Today, in this chapter, we are going to discuss about the following topics. The first one is Oester Experiment. So I already discussed Oester Experiment means the conclusion is that if you send current to a conductor, the magnetism will be produced. So that what the experiment he has done, the conclusions we can find in Oester Experiment. After that, the magnetic field, how the magnetic field will be created, what is the direction of that magnetic field, so that what is flux, what is the units, what is the relation between magnetic field and flux. The second one is the magnetic field due to currents. Magnetic field due to currents may be through a straight wire or circular coil or a solenoid. So if you send a current through these three equipments, how the magnetic field will be created. So what is the direction of magnetic field will be there. So we can see in this concept. The third one is magnetic force on a moving charge on a current carrying wire. So we already know that whenever a current passing through a conductor, there is a magnetic field surrounded by the conductor. So if you put that conductor, current carrying conductor, placed in a magnetic field, what is the force exist? What will happen? We have to know. So we can know that concept if you put one current carrying conductor in a magnetic field. So especially when two magnets are close to each other, that means two magnetic fields are close to each other, there may be a attractive force or may be a repulsive force. In the same way, when the current is passing through a conductor, there is a magnetic field, that is one magnetic field. If you put that conductor in another magnetic field, that is another magnetic field means another magnet. Suppose flux, because of this current carrying conductor, one magnetic field will be produced. If you put that conductor nearer to that another magnetic field, so the conductor will definitely experience a force. So at what direction the force will be created and how it will be, we can find the direction of that force, we can discuss in this concept. We already know that the force will be created, so that force will create that conductor makes a rotation. That means if a current passing through a conductor is placed in another magnetic field, it will experience a force. That force will helps to rotate that conductor. So that is the basic principle of electric motor. Electric motor. That means when you are giving electrical energy, the mechanical energy will be coming as a output. So that is the principle of DC motor. So that is electrical motor, which we discussed as a fourth topic. And coming to the fifth topic, electromagnetic induction. It is also very important concept. So whatever we are using, whatever the motors we are using in domestic way to pump the water from ground level to higher level, so those are all called induction motors. So how the induction motor will work, what is inside, so we are discussing here this fifth concept, that is electromagnetic induction. So only because of Faraday's law and Lenz's law. And finally, electric AC generator. Here DC motor, it is a generator. What is the difference between motor and generator is that in electrical motor we are giving electrical energy and we are taking mechanical energy as the output, but in AC generator we are giving mechanical energy as the input and we are getting electricity as the output. So that is the basic thing in the basic difference between electrical motor and electrical generator. So these are the main concept we are going to discuss in electromagnetism chapter. Right? Let us discuss about the Oester experiment. So in this Oester experiment, we require one thermocol sheet and two wooden sticks. U-shaped wooden sticks are required. U-shaped wooden sticks, and these will be attached to the thermocol. And we place one copper wire on these wooden sticks. So one copper wire on the wooden sticks, and one end of this copper wire will be connected to a switch and a battery, and this negative terminal is connected to another terminal of the copper wire. So the battery voltage may be V. This is a plus and minus symbols of the positive and negative terminal of this battery, and this switch may be K. Okay, and we need one compass. We need one compass here. So you already know the compass will shows the north direction, north and south direction. Okay, this is the experimental setup for providing Oester experiment. So we require one thermocol sheet and two wooden sticks, U-shaped wooden sticks. These should be stick to the thermocol, and we place one copper wire on two wooden sticks, and one terminal will be connected to battery through switch and another terminal will be connected to the negative terminal of the battery, and one compass needle will be placed under the copper wire. So before closing the switch, the circuit will be open circuited, so no current will flows through this copper wire. The needle of the compass will shows north and south direction and stay there. It will stay at north and south directions. After that, if I close the switch, what will happen? Because of that battery, because of this battery, some current will flow through it. So this is the current directions. The current will flow through copper wire. So if you observe this compass needle, before closing the switch, there is no deflection in the needle. After closing switch, because of this current flow through the copper wire, this deflection, this needle will start deflection. So Oester found this change, the deflection of needle is found with this experiment. He started gives the reason for it. So now the first question, what is the reason or why the needle is deflected? Right? Is there any change in the position of the compass needle? Means yes. The compass is deflected from one place to another place. Initially it is showing north and south direction. After passing current through a copper wire, the needle is changes to another position. Which force is responsible? The question is, which force is responsible? Which force is responsible for the deflection? Which force is the responsible for the deflection? Or if there is any current carrying conductor applies any force here? To understand this concept, there is a term magnetic field. Yes, Because of this current passing through a conductor, there is a magnetic field surrounded by this conductor. Due to this magnetic field, the compass is affected. So compass is nothing but inside there is a magnet. If another magnet is nearer to that compass, automatically if two magnets are close to each other, there may be attractive force or maybe repulsive force. Attractive force or repulsive force. Because of that force, the compass start deflecting. Okay. So what is the reason? Magnetic field. Magnetic field. So we have to understand this magnetic field again. Right. Here let's discuss about the magnetic field. Now I consider one magnet which is having south pole and north pole. To know the directions of these magnetic lines, we use one compass. Initially we have to take a one white paper. We have to place the compass on the white paper. It will goes the north direction and south direction. So put dots on north and south and remove that compass, and we place one magnet at that two north and south points. So like this, if you put compass at this point, it will give direction like this. So note this, put a dot on the arrow mark and lift that compass again and place at this dot point, and it is gives this direction. And put again dot and put a compass again at this dot point, it will give the direction like this. If you joining all those lines, it will give this direction. That means the magnetic lines start from north pole to south pole, and this one. Now from this side also, if you repeat the same thing, the magnetic lines will flow from north pole to south pole, and again this one. And if you compare like this, and one more point, these magnetic lines will never intersect each other. You have to remember, these magnetic field lines will never intersect each other. So arrow mark will be like this, and now. So when outside, the magnetic field lines will start from north pole to south pole, but coming to inside, that is inside the magnetic field, it is starts from south pole to north pole. Inside the magnet, it will be south pole to north pole. These are called magnetic lines of force. These are called magnetic lines of force. So the distance between, if you observe this distance between these two magnetic lines, that will gives the strength of this magnet. If the distance is very less and more lines are existed, that magnet is having much strength. That means the strength of the magnet is very high. Magnetic flux, we can define two terms here. One is magnetic flux and magnetic flux density. Here the magnetic flux represents the number of lines passing through. So the number of lines passing through a imagined plane in a field. So the magnetic flux is defined as the number of lines passing through a plane. The number of magnetic lines passing through a plane is called magnetic flux. That can be represented with the letter phi. That can be represented with the letter phi. And the second one is magnetic flux density. The magnetic flux density can be understood easily with, suppose if you come across the population density, it is defined as the number of population living in certain 1 kilometer square area. In the same way, the magnetic flux density can be defined as the number of magnetic lines passing through a particular square area. Suppose if you take one meter square area, how much magnetic lines are passing through that area is called magnetic flux density. The same as the population density. Suppose if you take population density of some certain city, we can't calculate total number in the citizen. So we take some certain area, suppose 1 kilometer square area we have to take, and the number of people are living there. So that is called the population density. In the same way, magnetic flux density is also same. So certain area, if we take certain area, the number of magnetic lines passing through that area is nothing but magnetic flux density. That can be represented as a magnetic flux density B, that is equal to the number of flux lines passing through certain area. So that is flux per area is called flux density. The units for flux can be represented as Webers and area will be meter square. So Weber, the units for flux density is Weber per meter square or 1 Tesla. This also is a Tesla is a great scientist name. Who is responsible for Asian machines. To remember the name of scientist, we can put unit as a Tesla for magnetic flux density. So here we are using two terms. One is magnetic flux, another one is the magnetic flux density. Now we are discussing about these two terms. One is magnetic flux, another one is the magnetic flux density. We already know that magnetic flux density is equal to the flux by area, flux per unit area. Here suppose the magnetic lines are in this direction. Magnetic lines are in this direction, or magnetic flux B density is like this, and magnetic flux lines are in this direction. Suppose if I put a coil or certain area of coil like this, all the magnetic lines are passing through this area. Now the flux density B is equal to phi by area. That means the number of lines passing through this particular area is nothing but a flux density. Suppose in another case, this is our magnetic lines. This is our magnetic lines directions. Now suppose my coil is making an angle like this. In the previous case, the magnetic lines pass through this coil or complete coil. The total lines are passing through this coil, and the axis of this coil is parallel to the magnetic field, magnetic flux lines, magnetic lines of forces. Here the axis of the coil making an angle with the magnetic flux theta. That means depends on that angle. Suppose a coil is making an angle theta with the magnetic lines of force, that is the axis of coil or plane is making an angle with the magnetic flux, then we can write the flux phi is equal to BA cos theta. BA cos theta. Suppose if theta is equal to 0, that means phi max is equal to BA. So when the theta will be 0, if the axis of the coil makes 0 degrees with the magnetic lines, dot product. Okay. So when theta is equal to 0, theta equal to 0 means, in this case, theta is equal to 0 means the magnetic lines are parallel with the axis of the coil. In this case, theta is equal to 0. So magnetic flux is equal to maximum, that is equal to flux density into area. But here, in this case, making theta degrees with the magnetic lines. That means magnetic flux phi is equal to BA some cos theta. Suppose theta is equal to 90 degrees. If the theta is equal to 90 degrees means what? This is the magnetic lines. If you are putting your coil, I will take another color. If you put coil in this way, that means the axis is in this direction, magnetic lines will be in this direction. So if you axis of the coil making 90 degrees with the magnetic flux lines. If here theta is equal to 90 degrees, so flux phi is equal to BA cos 90, that is equal to 0. Okay. Now in this way we can calculate. So what we can understand from this? If the plane is making 90 degrees, axis of the plane is making 90 degrees with the lines of force, no magnetic lines will be passed through this coil. If the no line is passing through that coil, what does that mean? Flux is 0. Flux is nothing but the number of magnetic lines of force passing through that plane. If the number of magnetic lines passing through that plane is 0, then flux is automatically 0. When it will be 0, the axis of the coil making 90 degrees with the magnetic lines of force, then flux is 0. So we can consider say dot product. So flux phi is equal to BA cos theta. It's very important. Okay, we have to remember magnetic flux and magnetic flux density. Magnetic flux is nothing but the number of lines passing through a plane. Or coming to the magnetic flux density, the number of lines passing through a plane which is having certain area. So that is called magnetic flux density. So this is magnetic flux. Phi max is equal to magnetic flux density into area of cross section, or phi is equal to BA cos theta. Okay.